Dear students, in the last class we have discussed about the intercalation compound of graphite with alkali metals, and today we are going to look into intercalation compounds of graphite with oxoacids and metal halides as well as oxides and sulfides as well as intercalation compound of graphite with halogens. So, first moving into the first topic, that is intercalation compound of oxoacids and metal halides with graphite. So, you can actually have these two classification. You can classify them into these two categories, but their basic structure and properties will be similar. So, intercalation compounds of oxoacids can be obtained by reacting graphite with concentrated oxoacids. So, you take graphite, you take concentrated oxoacids in oxygen or air, in the presence of oxygen or in the presence of air, to get the corresponding intercalation compound of oxoacids. So these compounds are called lamellar graphite salts, and HNO3, H2SO4 and several other oxoacids can form this kind of graphite intercalation compounds. Some examples for intercalation compounds of oxoacid are C24 plus NO3 minus dot 2H2O, 2HNO3, which is having a blue color, C48 plus NO3 minus dot 3HNO3, which is having a black color, etc. So the extent of intercalation depends on the strength of acid and its concentration. This is an important concept. So the extent of intercalation, how much intercalation occurs, that depends upon the strength of the acid that you're using and as well as the concentration. So in most of the cases, for better intercalation, you should use concentrated oxoacids. Now coming to the intercalation compounds of metal halides, in this they are prepared by reacting metal halides in the presence of free halogens with graphite. Graphite will be reacted with metal halides in the presence of free halogens. Corresponding halogens should be present there. These intercalated metal halides will be Lewis acids, and they can form first stage intercalation compound, second stage intercalation compound, third stage intercalation compound, etc. An example is given here. The first stage intercalation compound formed by graphite and ferrichloride is given here, that is C6 to 7 FeCl3 is the first stage intercalation compound formed by graphite and ferrichloride, and the second stage intercalation compound will be C12 FeCl3, and the third stage intercalation compound will be having a corresponding formula C24 to 30 FeCl3. So you can compare this to the other first stage, second stage and third stage intercalation compounds that you observed in the case of the graphite intercalation compounds of alkali metals. So in both of these cases, in the intercalation compounds of oxoacids as well as the metal halides, there appears to be a transfer of electrons from the host graphite. The electrons from the graphite will be transferred to the intercalated species. In here it is a Lewis acid, so they can accept the corresponding electrons, and there will be corresponding transfer of electrons from the graphite to the intercalated species, which leads to the formation of intercalation species of the type C24 plus HSO4 minus dot 2H2SO4. So the transfer of electrons will be imparting a particular charge to the particular intercalated or gas species in that particular graphite intercalation compound. And another example is C24 plus NO3 minus dot 2HNO3, or you can have C10 Cl minus C10 plus Cl minus dot FeCl2 dot 5 FeCl3, or C27 plus AlCl4 minus dot 2AlCl3. All these are examples for the formation of this kind of ionic kind of species by the transfer of electrons between the guest and the host. Guest is the corresponding species that is intercalated into the graphite layers, and the host is the graphite layer. The enhanced conductivity of these materials are due to the formation of positive holes near the valence band of graphite. So this kind of arrangement will be giving the graphite integration compounds of oxo acids or metahalides with graphites a superior conductivity property than the graphite. If you compare the conductivity of graphite and graphite integration compounds of oxo acids and metal halides, you can find these integrated compounds will be having higher conductivity. It's due to the formation of these kinds of holes near the graphitic or the near the valence band of graphite, or due to this kind of electronic transfers possible this kind of materials. So whenever you're talking about intercalation compounds of oxides and metal halides with graphite, you have to mention how they can be prepared, how they can be prepared, and about their structure, about the various properties. In both these cases, they will be Lewis acid kind of behavior will be observed for the gust, and you should mention about the electron transfer and electronic properties. Another important thing is you have to give some examples also. So important factors that you have to mention while you are mentioning about intercalation compounds of oxo acids and metal halides. So this is an example for the intercalation compound formed by graphite and FeCl3. You can see between the layers of graphite the FeCl3 will be placed. And these kind of materials, if you look into literature, if you look browse through the Google, you can see various kind of publications mentioning about this kind of materials, because they are having wide applications in electronics and all, in batteries and all. So if you just search, you can see publications that were published even after 2017 about these materials and the intercalation compounds of graphite and their importance. Now moving further to the intercalation compounds of oxides and sulfides. So about intercalation compound of oxides and sulfides, here also you will be having graphite. In between the graphitic layers, you will be incorporating the sulfides or oxides to form the intercalation compounds of the corresponding oxides and sulfides. You can actually form intercalation compounds of the oxides such as SO3, N2O5, Cl2O7, CrO3, MO3, etc. And sulfides such as vanadium sulfide, chromium sulfide, tungsten sulfide, lead sulfide, antimony sulfide, etc. So they can be intercalated into the graphite to form the intercalation compounds. And here you can see this is a publication. This publication actually mentions about the formation of intercalation compound of graphite with N2O5. How N2O5 intercalates to this particular material. So you can actually do the TEM studies, transmission electron microscopic studies, or XRD studies, to understand the intercalation, the extent of intercalation, how much change is occurring in the particular crystal or the structure of the graphite. Or extra can be understood using the XRD pattern or the TEM images, or you can actually do this kind of EDX analysis, etc. analyze the amount of various elements present in that material, etc. This is just for knowledge. If you look into various papers, you can see they will be doing, first they will be trying to prepare some compounds, and then they will be trying to analyze these compounds. For analysis, they will be using different kinds of techniques. So whenever you are studying various terms or concepts in physical chemistry and all, you will be wondering why I am studying this, because they, all these things, that is NMR, IR, UV, etc., all are important. X-ray studies are important to study a material, to understand whether you obtain that particular material. So here I just took a picture. So in this you can see the corresponding XRD data also. They are doing the XRD data, XRD study of graphite after a particular reaction, and they are reacting that material for different time periods with the reagents, so that they are getting different results. So the structure of the material is changing. They can, from the XRD itself, it's clear to them that the structure of the material is changing. I'm not going in deep into this particular thing, but you should know whenever you're trying to prepare some inorganic materials, you will be obviously going for TEM analysis or XRD analysis to study the particular structure of the compound. So this is the basic structure of the graphite intercalation compound formed by N2O5. You incorporate N2O5 into graphitic layers, you will be getting this kind of structures. So depending on the corresponding time of reaction time, corresponding amount of the reagent that you're using, you will be getting different compositions here also. So this is regarding the intercalation compounds of graphite, oxides and sulfides. And now moving on to another important kind of intercalation compound, that is intercalation compound of halogen. Halogens, as you all know, can have fluorine, chlorine, bromine, iodine, etc. are the important halogens. How they can be intercalated into the graphitic layers to form the graphite intercalation compounds. And here the important thing is chlorine and bromine reversibly intercalate into graphite. They can be reversibly intercalated into graphite to form intercalation compounds. Interhalogen compounds also form intercalation compounds, but iodine does not form intercalation compound. So you can have chlorine and bromine forming intercalation compounds. Iodine will not be forming intercalation compound, and in the case of fluorine, they will be reversibly forming intercalation compounds. Irreversibly forming intercalation compounds. So in the alkali metal intercalation as well as the oxide intercalation also, you were able to retain the properties of graphite by some method. You could do some you could do some process in order to get back the graphite. Those reactions were reversible actually. But in the case of fluorine, if you incorporate fluorine into graphitic layers, you cannot return back. You cannot turn back because it is an irreversible process. And actually, the intercalation compound formed by fluorine with graphite cannot be actually considered as a perfectly intercalation compound of graphite because it is not reversible, it is irreversible. But we are discussing that under this particular category itself. So they will be treated as treated with other names also. That is like carbon monofluoride, graphite monofluoride, etc. will be the terms used for indicating the intercalation compounds of fluorine with graphite. So now we are going to discuss in detail about the intercalation compounds of fluorine with graphite. The intercalation compounds of fluorine is also known as graphite monofluoride, carbon monofluoride, polycarbon fluoride or polycarbon monofluoride. They have the general formula CFN or CF common as whole n times. And they can be obtained by reacting graphite and fluorine at 400 to 600 degrees Celsius. In some texts you will be seeing 500 degrees Celsius. So you can do the reaction between graphite and fluorine in the range of 400 to 600 degrees Celsius to get the graphite intercalation compound, which has variable composition. As temperature varies, you will be getting the intercalation compounds of variable composition. As you vary the fluorine concentration, you will be getting different compositions of the intercalation compounds, etc. So this ratio, this composition, if you mention that CFN, this N can be between 0.7 to 1 or 0.6 to 1. This much variation can be possible for this N value when you intercalate graphite with fluorine. So carbon is stable in a fluorine atmosphere up to 400 degrees Celsius. So up to 400 degrees Celsius, if you keep the carbon or graphitic powder and powder in a fluorine atmosphere, it will not undergo any reaction because it is stable up to 400 degrees Celsius. But between 420 to 600 degrees Celsius, a reaction takes place to give substoichiometric carbon monofluoride CF.68 appearing dark gray color, which is having a dark gray color. With increasing temperature and fluorine pressure, stoichiometries up to CF 1.12 are formed. With increasing fluorine content, the color changes from dark gray to cream white. So as the fluorine content amount of fluorine is increased and increased and increased, we can see the dark gray color will be changing gradually from the dark gray color to a creamish white color, indicating the loss of aromatic character. So this color change is indicative of this aromatic character itself. So should remember how you can simply synthesize the graphite, that is by mixing, or you just have to keep graphite powder in fluorine atmosphere above a temperature of 400 degrees Celsius. Only above 400 degrees Celsius the graphite will be reactive and will be reacting with fluorine to form graphite monofluoride or carbon monofluoride. But there is one condition: if we change the temperature, if we increase the temperature about 600 degrees Celsius or about 800 degrees Celsius, there is a possibility for degradation of this compound to the corresponding fluorocarbons. So during this reaction, with increase in fluorine content, the color of the compound will be changing. As the fluorine content is increased, the aromatic character will be reduced and the dark gray colored compounds will be converted to creamish white colored due to the loss of aromatic character. With increasing temperature and fluorine pressure, stoichiometries up to CF 1.12 can be obtained. The fluorine atoms are located at an alternating fashion above and under the formation of former graphite plane. So if you have graphite plane, the fluorine will be present above and below the planes, which is now buckled due to the formation of covalent carbon-fluorine bonds. So as the fluorine amount is increased, these layers will be buckled and the aromatic character will be lost. Reaction of carbon with fluorine at even higher temperature successively destroys the graphite compound to yield a mixture of gaseous fluorocarbons. So here this is a graphical representation attempting to illustrate what happens when you heat the graphite powder with fluorine. So in the x-axis we are showing the fluorine concentration. Here you have the low fluorine concentration, here you have higher fluorine concentration, and the x-axis you are having the temperature. The x-axis you have the temperature. So up to 400 degrees Celsius there is no reaction. The graphite will be stable up to 400 degrees Celsius. At 420 degrees Celsius it will be starting to react. At lower fluorine concentration it will be reacting to give you the compounds corresponding to CF.68 ratios, which is having dark gray color. So at lower fluorine concentration you will be obviously getting dark colored compounds because the fluorine content is lower and the aromatic character is higher. But if you increase the temperature or increase the fluorine concentration, you can see the color changes from dark gray to cream white, and the highest stoichiometries will be obtained as you move from lower fluorine concentration to higher fluorine concentrations. And if you further increase the temperature also, you can see more and more reactivity and more formation of this kind of compounds. And after 600 degrees Celsius or 600 degrees Celsius, there's a possibility for formation of mixture of fluorocarbons, and obviously after 800 degrees Celsius you will be getting a mixture of gaseous fluorocarbons. So this is and this is not important to I am not compelling you to study this graph, but I use this because it will be easier for me to demonstrate what happens when you change the fluorine concentration and temperature. So here at lower temperature below 400 degrees Celsius, graphite will be stable, carbon will be stable, will not react with fluorine. And at lower fluorine concentration, it will react with fluorine to form carbon monofluoride with lower ratios of fluorine, which will be having dark colors. And at higher fluorine concentration, you will be getting creamish or whitish colored compounds, which is indicative of loss of aromatic nature. And the stoichiometries can be up to CF 1.12. And these reactions can occur in between 400 to 600 degrees Celsius, and above 600 degrees Celsius of temperature, mixture of gaseous fluorocarbons will be formed. And obviously, you cannot make the reactions to occur at a temperature beyond 800 degrees Celsius, because obviously you won't be getting any carbon monofluoride, you will be solely getting a mixture of gaseous fluorocarbons alone. So now moving into another important compound, that is C4F, which can be obtained by treating hydrogen fluoride and graphite. So you take HF, fluorine gas and graphite at room temperature, you will be getting C4F. When a mixture of fluorine, hydrogen fluoride reacts with powdered graphite at room temperature, bluish black intercalation compound. This intercalation compound is bluish black color, is predominantly formed, which has the composition C4F. The structure of C4F comprises of graphite sheets. These lines indicate graphite sheets with regularly spaced fluorine atoms. These are fluorine atoms above and below graphite layers. You will be having regularly spaced fluorine atoms above and below the graphite planes. In addition to C4F, some C2F will also be formed. Some small amount of C2F will also be formed. So this is another way in which we can form intercalation compound of fluorine with graphite. And now we can have intercalation compounds of chlorine, bromine, etc. with graphite. So they can be having composition like C8Cl, C8Br, C12Br, C16Br, C20Br, etc. And in addition to this, interhalogen compounds such as ClF3, BrF3, IF5, etc. can also form intercalation compounds with graphite. The ultimate thing that we are having today. So we discussed about the intercalation compounds that can be formed by halogens also. They can form intercalation compounds. Chlorine and bromine form reversibly intercalation compounds with graphite. Iodine will not form intercalation compounds. Interhalogen compounds can form intercalation compounds, but fluorine will be reacting irreversibly to form intercalation compounds with graphite. And the fluorine intercalated graphite is termed as carbon monofluoride or graphite monofluoride. In addition to that, they can be named as polycarbon fluoride, polycarbon monofluoride, etc. And we discussed how you can synthesize these compounds, how their structure will be varying with the varying composition of fluorine, how temperature affects the synthesis, etc. about the variation, the color of the compound that you obtain, the reason for variation of color, the difference in color that you obtain when you make this kind of compounds was also discussed. And we discussed about C4F, which is another compound which can be prepared by reacting graphite with hydrogen fluoride and fluorine gas. And this is a bluish black compound which is having graphite and fluorine atoms evenly spaced between graphite layers. And we also mentioned about the intercalation compounds that can be formed by chlorine, bromine, etc., as well as various interhalogen compounds also. So, as we already mentioned, the applications of graphite intercalation compounds will be coming under the electronic and electrical application. They will be having applications in batteries, and they can be having applications in catalysis also. In some cases, they will be showing some oxidative kind of behavior and catalyst activity. But important application is electronic and electrical applications, as well as their application in batteries also tremendous. So you can go through internet, go through Google, and find out various number of publications related to this kind of graphite intercalation compound, specifically alkali metal intercalated compound, the metal halide intercalated compound, etc. There will be large number of uh, publications related to the graphite intercalation compounds. Even recent publications related to graphite intercalation compounds can be found. And that's all regarding the intercalation compounds that is coming under our syllabus. And I hope it is clear to you. And thank you so much.